Morning, everyone. So we're going to be starting off our course with the review of some of the main concepts we did in Chem 11. I'm going to try to hit the concepts that we will be revisiting in this course here. We'll use it as a form of just introduction. Just like if we would do this in a real lesson here, I would encourage you to have out a notebook of your own, copy down the notes as we go through, especially as we get to practice problems here. As I write down the question, I would encourage you just to pause it, try the question out for yourself, and then you can just unpause the video and then check your work with me together. So this is just the beginning of our Chem 11 review here. Although we're not going to spend a whole other lesson just relearning safety here, I'm going to attach a link to my grade 11 safety lesson. I'd encourage you to just take a quick skim through there. Make sure you know things like, I'm just going to highlight it here. So for example, for safety, make sure you know what WMIS stands for. So WMIS, in our case here, it's the Workplace Hazardous Materials Information System. Right, so basically, for our safety standard, this is a Canadian standard introduced in the 1980s or so. It was recently updated in 2015, so we're sort of in this transitionary period where you might still see some of the older symbols, those 8 pictures. For example, let me just do one of them here. We call these ones here pictograms. So let's say there's a big O and there's a fire here. Hopefully you remember from the from our old WMIS lessons here. This one here actually stands for an oxidizing material. In this course here, we're actually going to learn towards the end, oxidation. Oxidizing actually comes from the reaction oxidation. Although we are going to be looking at oxidation as actually a loss of electrons as that type of reaction, one of the outcomes of an oxidation is it ends up releasing off oxygen. And what we know is we always need oxygen to burn, so that's why we always keep oxidizing and flammable materials together, so that if they unfortunately catch fire, they're just in a fire cabinet and sort of sealed away from the other chemicals that we have. So have another look over our WMIS lessons here to introduce some pictures that have changed. So for example, there was one where we had a T and then it almost looked like an exclamation mark. This one here was one of the poisonous categories here. This one here was really the catch-all. So this one was the one that contains other toxic effects. This was the one over long periods of time, over repeated exposure. That's another name that I like writing for there. In the new system, what they did is they actually separated this picture here. It was separated into just an exclamation mark. And another picture here, which is almost like there's a schematic of a person here, and you can sort of see the insides of his lung as well. And they're just trying to separate between the two different safety hazards. So this picture here, it's may cause serious health effects. So that's sort of focusing on you as a worker and working with that equipment there. The one with the exclamation mark here. This one also sort of talks about health effects here. This one has a terminology here. This one may cause less severe. So may cause less severe health effects. And they even throw in another one here. We always want to be sort of environmentally conscious here. For this one here, they actually talk about here, this chemical here may actually damage the ozone layer. So if I'm specifically looking at a chemical that might do that, might be given a slightly different picture. So just be aware the products, a lot of the products that we have from before will still be off our old WMIS standard here, but they're slowly going to transition over to some of the newer pictures. All right, so after we went through our safety, sort of the first big idea that we talked about was doing conversions between units. And just let me recap with you here for your conversions. Our general structure was we put question mark with the unit that we want. We're usually given a unit already, so this is the one that we have. How we're going to accomplish our unit conversion is we're actually going to set up a fraction, and by multiplying by this fraction here, we can actually get the units that we want here to actually cancel out. So half, put the half down below, top cancels bottom, and then we're going to get to what we want up above. As we start looking through a few practice questions again, we're going to see we can tack on as many fractions one after the other, as long as your final units are the ones that we end up with. Just let me rehash with you here. Depending on the context and sort of the power of 10 that we're interested in, we have what are called prefaces, and we have our SI sort of base units here. Prefaces are little syllables that come before the word here. They give you a rough power of 10. Without getting into all of them here, let's just start off from kilo. Kilo by itself with the K. This one here stands for 10 to the 3. For positive powers of 10, it just talks about how many zeros come afterwards. You can mix and match any of these prefaces here with our base units. Our base units in chemistry, if we're interested in measuring a length, we're going to measure it in meters. If we're interested in measuring a mass, we're going to measure that in kilograms. That is the correct SI unit, although remember in chemistry, the SI unit is switched to just grams. I like that because it actually points to you that the kilo part isn't actually special to grams. I can have a kilometer, or next is going to be a kilosecond here. Kilo is just a prefix that gives you a rough power of 10, so it's not sort of stuck on any particular base unit. So looking at powers of 10 here, we went from 1,000. Let's step down in powers of 10. So the next one down is hecto. So this is 10 to the 2. The one above and below the base unit. The base unit here actually has no prefix. So if you don't have a prefix at all, this is just times 10 to the 1. We have deca up above, and we have deci down below. So deci, we're going to shorthand that d. Deca is going to be dA. Deca is going to be 10 to the power 1, whereas deci here is actually into the negative powers. 10 to the negative 1, that means 1 over 10, or in decimals, it means 0.1. So again, depending on your context here, you'll know roughly what power we're talking about here. If I break up a meter into 100 segments here, we get a centimeter. So centi is the prefix for 10 to the minus 2. If I take one of those centimeters and chop it up into 10 again, this one here would then give you millimeters. The most common ones that they ask you are definitely going to be the kilo, which is sort of 1,000 bigger, milli, which is 1,000 smaller. When you're actually writing out some of these conversions, we'll practice a little bit of this here. Usually we write one of the big things. So let's say I have 1 kilometer. Well, kilo means 1,000, so that then means 1,000 meters. If I have 1 millimeter like this, although milli, the prefix is 10 to the negative 3, what it's suggesting is it's suggesting you to write 1 millimeter is actually 10 to the negative 3 of a meter. I generally find people have a little bit more trouble with negative powers. So what I tell people is, no, let's put a 1 beside the bigger unit, and then even if the prefix milli, in this case here, would have had a negative power, the negative power now switches over to become a positive power. So I actually need 1,000 tiny little millimeters to make up 1 meter. It's basically like a milli is 1,000th of a meter. I need 1,000 thousandths of a meter to end up giving one big guy there. Right? So let's just practice through a unit conversion here. In our first chapter in Chem 12, it also will deal with these sort of unit conversions, so it's definitely good to practice. This one here I didn't quite get to introducing, but we'll just do it here. This mu symbol, this mu actually stands for 10 to the negative 6. It stands for a micrometer. And in this question here, what we're interested in is trying to convert between this micrometer into centimeters. We want to convert one prefix to the other prefix. Without the table in front of you and just counting the number of steps, remember our strategy was let's just go back to the base unit first, and then let's go from the base unit to the new unit here. So let's try it out here. Question mark centimeters, because I know my final answer should be centimeters. If you're ever stuck, just start off with the unit given, which is 12.3 micrometers. What I want to say is I want to go micrometers on the bottom so that unit cancels out. I want to say centimeters on top, but like we just mentioned, I may not know that conversion. So let's go micro just straight back into meter first, and then let's go from meter over into centimeters. Top unit cancels bottom unit. Let's go through and stick a 1 beside the unit that's bigger. So a meter is definitely way bigger than a micrometer. Between centimeters and meters, well, meter is bigger here. And then we just look at our chart or just memorize from our table here. Well, micro by itself means 10 to the negative 6. Because I stuck a 1 beside the bigger thing, the negative power now becomes positive. I need many, many millionths of a meter to end up giving you one big meter here. And similarly here, centi, earlier we had said 10 to the negative 2. The power just becomes positive 2. You can write that out here as 100 if you like. So what I'm going to do here, so far in just powers of 10, I'm going to pick up 2 powers. I'm going to lose 6. So in total, I'm going to lose 4. It would be 12.3 times 10 to the negative 4, because I'm going to lose 4 powers. Numbers on top you multiply, on the bottom you divide. That's not quite proper scientific notation. Scientific notation should have the first digit just between 1 and 9. So if I just move the decimal place over a little bit here, 1.23 times 10 to the negative 3, numerically that value is the same, and now we have it in scientific notation. Really useful for writing really big numbers and really small numbers. Sometimes they even call this one here exponential notation. Remember, for scientific notation, these numbers here are called base numbers. All base numbers are significant. So in terms of our significant digits and meaningful digits, the ones that I want to keep around here, everything that I write on the base number here is significant there. Let's do one more unit conversion, and then we'll recap significant figures. It's possible that you may actually have a fraction. So let's say I have 45 grams per second. So let's just think through that dimensionally here. So this is talking about mass change as time goes onward. So this could be a measure of reaction rate. So I lose reactant at this speed, or I gain products at this speed here. Let's see if we can switch this over here. How many would this number be if I re-expressed it as, let's say, milligrams per minute? Right? So don't get too scared away here. Whenever there's a fraction in the unit, all you're going to do is you're going to write out that fraction here explicitly. So the 45 sticks with the unit on top. So this is going to be 45 grams. When you just say per second, what you mean is all over 1 second. So that's actually where we're starting with. Now, because it's a fraction, we can now just think about, let's convert the gram over to the milligram. Well, gram is on top. I don't want it. Stick it down below. Grams on the bottom, milligrams on top. And then I can convert the bottom unit here. Order doesn't matter. So seconds going to minutes. The only little trick here is because seconds was already on the bottom for the per second, we actually want to have seconds on top and then put the minutes down below here. So let's go through here. Let's take a 1 beside the unit that's bigger. Gram is bigger than a milligram. Minute is bigger than a second. Especially as we do these conversions here, if ever one of these is a 1, we can sometimes refer to this as a unitary rate. So some problems may say use unitary rates to solve it. It's essentially the way we're doing it, where we put a 1 beside the thing that's bigger. Again, milli from earlier, millis over 10 to the negative 3, but because I put a 1 beside the bigger thing, now I need 1,000 thousandths of a meter. I need a huge number of tiny little guys to make one big guy. Most of our prefixes have been just powers of 10, so it's just basically moving the decimal place around. We will encounter other conversions, let's say minutes and seconds. Well, 1 minute is actually 60 seconds. And then based on the way the units have to cancel out, numbers on top you multiply. So I'm going to go 45 times 1,000 times 60. I'm not going to bother typing any divide by ones. This one here is a 2 sig fig number, so let's just convert it here. 2.7 times 10 to the 6. And my units are now going to be milligrams per minute, because those are the units that were left over. So as we introduce here in terms of significant figures, when we first look at these numbers here, like 1,000 or 60 here, those definitely do look like 1 sig fig numbers, but you have to remember here, both of these are by definition. So we define milli to be exactly 1,000, not 999, not 1,000.1, something like that, but these two are by definition, meaning these two are exact. There's no imprecision here. All we really have here is a 2 sig fig number. The 45, yeah, I'm not really sure about that 5 there. It could be 46, could be 47. This is a 2 sig fig number. We want to make sure that our final answer represents the similar precision as was going into it. So this gets us back into our significant figures. So significant figures, or what I refer to as significant digits here. Significant figures are the meaningful digits. Remember, calculator doesn't know anything about significant figures here. This is why we take the answer out of the calculator and we might need to still round it. There were sort of two main rules for significant figures here. In addition to sort of definitions, these are exact, so you don't need to worry about significant figures. For the measurements that we take, the operations were if we add and subtract. Right. This one here, we kept it very simple for us here. We just said keep the lowest decimal places. So for example, if I take a number 6.7 plus 8.90, right? So if these ones here are measurements, I'll say both of these are, let's say, centimeters here. This 6.7, although I was not the experimenter, I can read this, well, this is a 2 sig fig number, meaning even though I'm certain of the 6 here, I'm actually eyeballing and I'm guessing this 7 here. That could really be 6.8, 6.9, not really sure. This 8.90, I look at it, well, you have more decimal places. It should be more precise. That means I'm certain of the 8, the 9, and I'm actually guessing at that 0 here. For the meaningful digits here, it contains all the certain ones, all the ones I'm sure of, but we're allowed to keep around one guess. We could totally be wrong with that guess there, but it still gives me some information. The whole emphasis there is it's only one guess, not 2 guesses, not 10 guesses. You can do that in your calculator. So let's go 6.7, add 8.9. Calculator will spit out an exact 15.6 because the calculator thinks exact 6.7, exact 8.90. It thinks exact 15.6 all the way 0 to infinity. When I'm doing the rounding here, I'm going to say, well, wait a second. If this one here were off, if this was actually 6.8, that would knock off this digit. Even if I were tempted at first to write this number as 15.60, I would then want to round it here. If I want to round it back to this position, so I do actually want to write it as 15.6, and therefore this number here has one decimal place, like the one that has least decimal places. That rule was a little bit more interesting. When we go to multiply and divide, it gets a little bit easier. Fortunately, a lot of our conversions are these unit conversions, unitary rates. They're all these fractions. So we go straight to this rule here. For multiply and divide, numbers get big fast and they get small fast here. We're going to keep the least significant figures. We're not going to bother lining up the decimals and try to match up which ones in precise to where. We actually just take a look at the numbers going into it. Let's do the numbers here. Let's go 4 times it by 5.00, maybe like that. Okay. So calculator doesn't know. Calculator just says, okay, 4 times 5, 20. Fine. But again, when I write out the number, I always want to write it out with the same precision as the numbers going into it. So if I have number 4.0, remember digits between 1 and 9 are always important. It's the zeros that are going to be problematic. For the zeros here, we use what's called the arrow rule. If I have a number that does not have a decimal place, the arrow shoots to the right. The arrow shoots to the left here. Everything that's cut off by this arrow here is non-significant. That only leaves me with this 5 here. If I have a number here with a decimal place, the arrow shoots to the right here. It gets stopped by anything that's not a 0, and therefore we have 1, 2, 3, 4. That means certain, 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 and that means we have a guess here. The numerical value in both of these numbers here is 500, but this one here is written with a lot more precision. This is like uncertain, 500.1, 500.2, whereas earlier when I have 500 like this, these zeros here are referred to as placeholders. They're still important because the 5 has to be in the hundreds position, but I'm really not sure of this one and only number that I have. Maybe we're talking 600 or 700 here. So if I do the arrow rule here, both of these numbers here have a decimal place. The arrow shoots to the right. That means this number here has 2 sig figs. This number here has 3 sig figs. The least precise one would be 2 sig figs. When I write a number 20, even though the calculator thinks an exact 20, so far it looks like 1 sig fig. How would I write this number so that it looks like it actually has 2 sig figs? Chemists do this annoying thing here. Well, because there's no decimal, the arrow would say that 0 is unimportant. Let's just put on a decimal. Usually, if I have a decimal, it's usually point something. And in this case here, because I only want to keep these 2 digits, I don't want to say 0.0, so I end up with 3 sig figs. If you want to just save yourself the hassle of doing this, what is this sort of decimal but nothing afterwards, you can just convert it directly into scientific notation, as we just rehashed here. In scientific notation, all the base numbers there are important. Okay, so lots of calculations. We're going to be introducing sort of those sig fig rules again here. Make sure you get a little bit of practice from our package. Let's just rehash over a little bit of the vocabulary. So chemistry is basically the study of matter. So matter, as we know, is things that have mass and volume. It's things that mass is it's made out of material, it's made out of substance, and it takes up volume, which is it takes up some space. Depending on the state of matter, solids, liquids, and gases, they all take different amounts of room. Because there's so much variety in matter here, we need a way to sort of categorize the matter. So let me just rehash for you some of the main words here. Our periodic table is the periodic table of elements. The element just refers to having one type of material. So for example, carbon is a material, hydrogen is a material, silver is a material. Each of them, yes, they have their own atom. We knew from our atomic structure unit from last year, it's the proton number that actually made them different. Pretty much if you have a box for it on the periodic table, it is an element. Let's now contrast the word element here with a compound. Both of these are referred to as pure substances, even though compounds are 2 or more types, right? So if I take let's say the C kind and the H kind, and I just bond them together, well, isn't that impure? Isn't that like, well, I have a C kind and H kind? It's true. The C and the H are totally different, but the emphasis here is to stay as a pure substance here. Two or more types, they hang out together, they're bonded together. So they just sort of stick together here. So as long as my container are just full of these CH groupings here, yes, I know the C is different from the H, but still in my container, we're just a box full of CH. We refer to these ones here as still pure substances because they hang out together. When you contrast the sort of two words here, element and compound, we can contrast it with the two words here, atom and molecule. First thing to note is both of these words here, they imply we're electrically neutral. So sometimes they're a little bit redundant and say, let's picture a neutral atom or neutral molecule. The words themselves already mean neutral. Neutral doesn't mean we can't have any charges, but it is good to emphasize here we have the same number of protons and electrons. So an atom here, instead of referring to the type of material, element is one kind, compound is more than one kind, an atom is just you have one particle. It's one of these spheres sitting in front of you, whereas a molecule is just more than one that's bonded together. So two or more, they could be different types, fine, or they could be the same, two or more atoms bonded together. So we learned these bonds here are made out of electrons. Two electrons make up a bond, and basically the electrons are attracted to the nuclei on both sides here. That would be equivalent of a covalent bond. We're going to rehash ionic bonds in a second here. So when we start looking at atom and molecule, we're looking at counting numbers. An atom is just one, whereas a molecule is more than one. So for a compound, because we have to have two types, automatically you're going to be a molecule because you have two or more things attached. However, we had some things called diatomics. Let's just actually go back to our periodic table here. Most of our elements actually occur to us monatomic. There are a few elements here, so keep note of these ones here. Let's say hydrogen. Hydrogen is actually unstable by itself. So when hydrogen actually occurs in nature, although they call it hydrogen gas, telling you it's a gas really doesn't change the fact that it's hydrogen. In this case here, the H atom is unstable by itself because it has an unpaired electron. It will very quickly pair up with another H. This one here is only an element because we only have the H kind. I've only chosen this square on the periodic table. But we are definitely a molecule here because we actually have more than one of the H's. They hang out together, they're stuck together, and they are grouped. So the ones that are diatomic here, it's this H here in the corner. We have on this side here, it almost looks like a 7, NO and F, Cl, Br, and iodine. These ones here, whenever they are by themselves, they always occur as diatomics. So make sure you take note of these ones here. They are diatomics. They are paired when they're element, when they're by themselves. When they're not by themselves, I'm not worried about them. So for example, I can have a compound like HF. You're not going to tell me, well, I thought H was diatomic and F was diatomic here. Well, the H is not by itself. It's not pure hydrogen anymore, but the H is actually being stabilized by the fluorine there. Again, we just assume everything is electrically neutral. So therefore, we have the number of protons match up to the number of electrons, especially as things start bonding, regardless if it's ionic or covalent bonding. Usually what we do is we play around with the electrons, especially in the case of ionic. When things actually lose electrons, they're going to end up forming ions in general. They refer to charged particles. In that situation that I just alluded to here, for something that loses electrons, they throw away negative things. They're going to end up becoming cations. Cations are positive. That means they have more protons than electrons, versus if I gain negative things, if I gain electrons, I'm actually going to end up as an anion. Anions are actually negatively charged. The number of protons are now less than the number of electrons. So sort of it's the interplay between do I have more positives or more negatives here that indicates to me the charge that we have. Just like last year, I actually gave you the periodic table from the grade 12 data booklet here. Remember, one big difference from the grade 11-12 table with the Science 9, Science 10 tables is they don't give you as much information. So we don't have sort of at the top of every corner here sort of all the combining capacities, all the charges. There are some that we need to memorize. So let's just do a quick recap over some of the basic trends on the periodic table. We know that we have a stair-step line. Stair-step line here divides on the left-hand side here. The left-hand side, we refer to these ones here as metals. Can you list off some properties that we know for metals? So metals, generally speaking, they're going to be solids in our regular everyday exposure of them. It's not impossible to get a liquid metal or a gaseous metal. It's just that you need to be much hotter, probably at much higher pressures. So we have a solid. These ones here tend to be flexible in some sense. So we can say that they are malleable. You take a mallet to them, they flatten out in sheets. Or they can be ductile. You start prying in them from both ends here. They don't crack or fracture on you here. They start stretching out into nice wires. So that's the property called ductility. As we go downwards here, metals tend to be good conductors. For conductors, we're going to refer to both a heat conduction as well as an electrical conduction here. Nicely, metals are good at both. We make our frying pans out of metal because it doesn't take forever to heat up, and definitely we make our wiring out of copper is the most general metal that we're going to talk about, but they allow charges to move really freely here. Definitely all metals in general should be conductive, but they're going to range in terms of which is most conductive and less conductive. Those are our metals on the left-hand side here. Let's contrast them with the nonmetals on the right-hand side. So here we have our nonmetals. Pretty much the opposite properties as metals. As opposed to looking like a solid, these ones here are typically going to be gases or liquids at room temperature. It's not that their covalent bonds inside are really weak. It's just that because they're covalently bonded, they just have really weak intermolecular forces. If you remember, we talked about those London forces and van der Waals forces. Those background attractions are actually really not really strong in holding the molecules together. So even by room temperature here, these ones have very quickly vaporized off. Instead of being malleable and ductile, those ones there refer to it being very flexible and sort of stretchy in some sense. Malleable here, for nonmetals, we actually have it being very brittle. It's very fragile. It's very, it will fracture on you. Now, again, we don't have a very everyday exposure to this. Like we just said, we're expecting these to be gases at room temperature. I would hate for you to take a hammer and start waving it around just the air, hoping to try to break up the carbon dioxide oxygen. You won't hit it. Basically, for you to actually get a feel of this here, you need to take the, let's say, gas nitrogen here. I need to cool it down to some negative 150, 180 or so before it starts liquefying. That's when we get liquid nitrogen. Keep cooling it down until we get a solid chunk of nitrogen. For that solid chunk of nitrogen, yes, if you take a hammer to it, it will shatter and it will fracture on you, and that one there would be brittle. For conductivity here, you can just say poor conductor, or sort of the contrast here, we can say they're insulators. They don't carry charges really well. Again, we're going to see for covalent bonds, because the electrons don't get transferred, we're sharing electrons, there's no charges that end up developing, so there's no reason for it to actually carry a current. Those are just going to be more simple molecules. We have in the stair step here, we call these ones here metalloids. They sort of have properties of both metals and nonmetals. So they may be malleable, but they may be an insulator, or they may be a good conductor, but they may be gas room temperature. They sort of have a sort of crisscross in properties. In terms of the charges that we have to memorize, we learned a couple different family names here. We talk about groups on the periodic table. So the groups are the up and down, the columns here. The first group here is referred to as the alkali metals. All the alkali metals, when bonding, they all take on a +1 charge. The alkaline earth metals right beside them, alkaline earth metals is group number 2. These will take on a +2. Remember, these are the charges only when bonding. So if someone hands you a block of lithium, that's fine. That can be lithium here with the no charge, right? It's neutral, right? Things like being neutral. It doesn't want to be charged. It wants to match up positive and negative. However, when lithium actually starts bonding, because it's in the alkali metal family, the lithium will take on a +1 charge. It will have to lose an electron. We say it gets oxidized. Usually when you lose things, the number goes lower, but it's actually the things that we're losing. We actually lose electrons, toss away negative things, end up making me more and more positive. Let's jump over to the opposite side here. We have our noble gases, so helium down to radon as a noble gas here. Those ones, we did our atomic structure section. Because they have a full valence shell, there's something about a full valence shell that ends up making them stable. So the noble gases themselves really don't like bonding, right? We found in very rare instances here, the larger of the noble gases, we can sort of force them to bond. So they've, within the last 10, 15 years or so, they managed to make a xenon actually bond, but otherwise, noble gases should be 0. The halogens, which are sort of one column right beside them, they're just one short of having a noble gas configuration, so these ones here will take on a -1 charge. Not only are they diatomic, they come out pair in nature, especially when they start bonding, they're going to take on a -1. And just sort of looking at that pattern here, if you had to guess, the oxygen column here, these ones here would be -2, the nitrogen column here would be -3. We're basically counting how many columns until we look like a noble gas. The noble gases are enjoying that stability. I want to play around with my electrons until I have that orientation. So make sure you know some of those there. For the transition metals here, which typically are multivalent, which typically have more than one charge, you're not asked to memorize all the charges here. On the back of the periodic table, you'll be listed. For example, iron can be +3 or +2. Instead of having a box here and actually listing it +3, +2, it's just going to tell you on the back, okay, iron could be 3 or 2. That's when we actually need to use Roman numerals for that. So those ones are a little more challenging. In general, those transition metals we refer to as multivalent. They actually have more than one charge. So let's just finish off this lesson here. Let's just recap a little bit of nomenclature. Nomenclature is a very fancy word. Essentially, all they're talking about here is just naming compounds. And in fact, there's a group, it's an International Union of Chemists. They call them IUPAC. So sometimes they talk about, give me the IUPAC name of this, the IUPAC nomenclature. It's basically the naming system that we've learned. So let's just switch over to looking at ionic compounds. To recognize something as an ionic compound, we can just go back to our earlier science classes. We're looking for a metal and a nonmetal. The metal always comes first. And the general name for this one here, if I just write it in a little more detail, metals actually lose some number of electrons until they look like a noble gas. Metals lose electrons to nonmetals. And again, in general, when we think of loss, we think of, oh, I'm actually going to go down. But in this case, the E minus, the electrons that I have actually have negative. If metals start off neutral and they throw away things that are more and more negative, the metals typically then take on a positive charge. The nonmetals, which are now gaining those electrons, will take on a negative charge here. And therefore, they form a nice sort of matched pair, positive and negative. Remember, for ionic compounds here, they always, so we talk about there's an electron transfer. We always talk about ionic compounds as forming a crystal lattice. That word crystal just means it's a repeating pattern. It's a nice orientation. Lattice is essentially this notion. It's repeating positive and negative. So what's happening here? Let's take lithium as an example. Lithium has one electron in its outermost shell. Let's counterbalance it with fluorine here. Just going to draw the outer shell for you here. So first thing that's going to happen is they have to collide, or else they don't even know each other present. They could, it's usually the unpaired electrons that do the bonding. They could have shared these electrons. We learned a property in grade 11 called electronegativity. We learned that fluorine is actually way more electronegative than lithium. I believe the electronegativity, let me just look it up here. So lithium here has an electronegativity of 1.0. Okay, this property here describes its ability to tug of war electrons within a bond here. What we care here is the difference in electronegativity. How uneven is this tug of war here? We go bigger number minus smaller number. This difference here is a 3. The fluorine is pulling way harder from lithium, and usually we threw around a number like 1.7, 1.8. When the tug of war gets to be more uneven than, let's say, 1.8, the fluorine is actually going to pull the electron completely over. We end up getting lithium, which is a positive charge, and then we have fluorine stealing lithium's electrons here. Fluorine acquires a full negative charge. Yes, this compound here just needs to be one Li and one F, but these charges are a little bit greedy. They actually already have counterbalance their charge, but because opposites attract, this lithium is actually going to surround itself with as many fluoride negatives around as possible. Let's just do that there. And the fluorides that are negative will counterbalance themselves with as many lithium positives. They may not necessarily be one on top of the other, but they definitely form this repeating pattern. This sort of repeats in 3D space. So we can have trillions and trillions and trillions of these atoms. What we care then is, well, what's the ratio? Well, if I know there's going to be millions and millions per how many lithium is how many fluorines, well, we had already worked out. Because of the +1 and -1, they already canceled out. This is referred to as the formula unit. It's sort of like the empirical formula. It's the Lego block that we're based off of. It just represents sort of the ratio between the positives and negatives, and that's why we can just say LiF. Metal comes first, non-metal comes afterwards. We're going to call this one here lithium fluoride. So all ionic compounds here end up forming these lattices here. Notice we changed the ending to IDE. So That one there I would just refer to as a binary compound because it's just basic metal and then non-metal. And then what we're going to throw in here, let's throw in our multivalent guys. So sort of the second little level of complexity here. Multivalent, especially for our metals, especially for our metals here, these are those transition metals here that could have multiple charges. For this one here, the general format likewise is going to be metal comes first, but we are going to have to add a Roman numeral, and that Roman numeral will actually indicate to you which charge is that metal using. Then we have the non-metal afterwards. We change the ending to IDE. So earlier I was saying iron could be using its +3 or iron could be using its +2. Let's bond iron with oxygen as an example. Depending on which charge it is, the rule is we need to transfer electrons until the sum of charges equals 0, until the positives cancel the negatives. So the iron +2 and the iron -2 here, this one's a little bit easier. That one would just become FeO, right? In that case there, I would call it iron. Well, when it's using its 2+ charge here, we're actually going to call it iron 2 oxide. So let's just point that one there. And for the other one here, if it actually uses its +3, 3 and 2 both go into 6. So I need 2 irons. So I'm going to go Fe2 to get this to 6. So I need 3 oxygens here. We won't come back to this and we won't say, oh, oxygen here, shouldn't it be diatomic? O2. It's not oxygen by itself. This is oxygen being stabilized by iron. It's just in words here, instead of just calling it iron oxide, both of these are iron oxide. This is actually iron using its 3 charge. And that 3 doesn't refer to how many irons are in the compound. I can work out that number later on. That Roman numeral actually indicates which charge the transition metal is using. So that one there's iron 3 oxide. We'll end off with one other layer of complexity here. Let's throw on a polyatomic. So polyatomic ions. Poly meaning there's many. Atomic, many atoms together. So for that just means a molecule. But somehow these ones here are actually charged. In junior science, we typically call these ones here PAI. So if you just see that, that's what they talk about. These ones here pretty much are given their own common name. And because they have a common name, I'm not going to try to name it myself. So for example, I might have the grouping here. We'll end off with this one here. NH4 2SO4 like this. Before you attempted to say nitrogen, hydrogen, sulfur oxide, something like that, it's usually just going to be a 1-part name for the positive bit, a 1-part name for the negative bit. Especially if I have more than one of a polyatomic grouping, I have to have a bracket here. Even though this SO4 is also a polyatomic here, because I just have one of them, chemists are lazy, I don't want to have brackets there. So what you're going to do is you're going to look on the back of your periodic table. We actually realize NH4 plus is actually the common name for ammonium. In fact, that NH4 plus actually has covalent bonds inside. So it's N attached to 4 other H's. We had talked about the bonding back in grade 11. I'm not going to need to worry too much about Lewis structures like that, but what I want to emphasize here is polyatomics, they have covalent bonds inside. We'll talk more about covalent bonds in tomorrow's lesson. But they're covalent bonds inside, but somehow because we still end up having charge, when I mix and match that with the sulfate grouping, the sulfate actually has an overall -2. We can still work this out in terms of ionic charges here. Well, how many ammoniums would I need to counterbalance sulfate? I need 2 of these whole NH4 groupings. I need to put the NH4 in brackets to remind me, no, it's the entire NH4 that I'm doubling up. Both of the NH4s just have a plus charge, and even though this ends up forming a lattice, even though this one ends up repeating over and over again, I know the ratio is for every 2, there has to be 1 SO4. SO4 is going to be sulfate. You can spell sulfate with either an F there or a PH. Polyatomics will either end in AT or ITE. We will not change it to IDE just to make a difference from before. This molecule here, as I demonstrated for you, the polyatomics themselves have covalent bonds inside, but it has an ionic attraction between the positive ammonium and the sulfate that's negative. So sometimes on multiple choice they might say, which one of these molecules contain both covalent and ionic? We're looking for an ionic compound that actually has a polyatomic. Right? So I'm going to leave it off there. Practice a little bit of the naming here. We'll finish that part off in tomorrow's lesson, and then we'll go from there. Thanks, guys.